Yeah. Okay, we have the problem with the local net the other day, so we have to stop before finishing. So we were discussing error propagation, and the main result is that for ordinary differential equations, the difference between the exact solution and the approximation has this form. So it's the approximation plus the time interval to the p times a function which only depends on time. Oh, sorry. Yeah. Sorry, I'm not sharing the screen. And I have to go out from here to do this. 1 second. So this is from the other day. This will do like this. And now we go to the other screen. Okay. Now you see it. Okay. So I was saying that we have a theorem that tells us that the exact solution is equal to the approximation, the numerical approximation of order p. So this Bn was something. Bn. Sometimes this have a very I don't know how to correct this. Maybe if I change colors, we'll do it. No. Okay. Bn plus 1 was Bn plus delta t a to the p. And this, remember, we were doing the one-step methods. And so this method was order p. So in that case, the exact solution is the approximation plus a term which is delta t to the p times phi t. And this depends only on ut and its derivatives. And of course, u and f through u. So we knew that we could use this this property to compute some quantities that we could use to check that it was true. So that we were in the regime where the system was converging and this term was small. And to do that, what we did was to compute this factor q, either using an exact solution and comparing the exact solution with the approximation, making it to be of this is the solution with delta t, and this is the solution with delta t over 2. So when you do this calculation, use these formulas, you get that this quantity, this ratio is 2 to the p. So for instance, for Runge-Kutta 4, you expect this number to be 16. And in general, you will see that sometimes it's 16, sometimes goes up, sometimes goes down, goes to 32, say. And this, you can explain more or less what happens. When we are here, it means that this term is too big. When we are here, it means that sometimes this term gets very small. You get a 0 from here, and then you have some jumps. Because actually the theory tells you that this is like, this other term is like also delta t to the p plus 1 plus some phi 2 of t. So sometimes this vanishes and you get the next term. So that's why sometimes it jumps. But this you will see in the labs. There is another school now that they are doing infectious modeling. So you can get this equation here that order differential equations and put in the lab things you have. So you can solve these ones if you want. We will take a picture so that we have it big enough. So, and then if we didn't have a exact solution, we could do this with delta t over 2 and delta t over 4, so for 3 runs. And use this quotient, and if you do that quotient, you get also the 2 to the p. So in practice, this is what is done usually. But if you do that, you could do something better than any of these solutions, and it's take into combinations. Because, for instance, you can take, say, this solution, and here you have a factor between this and this term. You have a factor 1 over 2 to the p. So you can multiply this by 2 to the p and subtract to that, and so you cancel this error and you get the next error, right? So if you write say Bn minus 2 to the p Bn minus 1, right? It's Bn, no, Bn minus 1, B2n. This is with 1, this is 1 half. So you subtract these two, this give you ut times a factor 1 minus 2 to the p, right, from these two, and this is equal plus some error order delta t to the p plus 1. Right, so now if you rewrite this, you get u to the p, ut to the p is equal to 1 over 1 minus 2 to the p times this factor here. I think I make some mistake, but these are like calculations like this. Here is the formula. But no, it's okay. It was okay. So this is a better approximation. one order better, and you gain it just by computing these two approximations and subtracting them. And this is called, if you will find that this is called extrapolation. Sometimes a Richardson extrapolation. I think that's the name. So you see, it's very important to this error theory because it allows in practice to know that you are doing things okay. So in general, when you do, it's a good practice when you are solving problems to check this Q and if you are checking the Q, you can check that this is a better solution. So now we are going to another point, which is important and we discussed already a bit, and what that was a stability region. Namely the region where if you look at the equation dy dt equals to lambda y, and then you do your one-step method. Remember, this was bn plus 1 equals to the bn plus delta t ap of bn delta t we have to put here too. We have this method and we solve this equation, and when we doing that, right, when we put the y, we can compute what this thing is, and you will get something like bn plus 1 is equal to some factor, let's call a times bn to the n bn, right? And this is the absolute value of this quantity that we call the amplification factor, because you know that the solution of this will be so here I was thinking this factor doesn't have this. The solution of this will be a to the n times b0. So we want to know whether this number grows or stays bounded. So the question is, for what region is this less than 1? And if we are in a system, it should be with like a norm, right? Not an absolute value, but it's enough to do for each method to do this for one variable, right? So we are looking for this amplification factor. In Euler's method, the amplification factor is this is A, where mu, remember, is lambda times delta t. So this is the amplification factor. So we have to look at the region working here, I don't have enough space to write things. So we have to look for the region where 1 plus mu is less than 1, right? So if we write this as minus mu minus 1, less than 1, so this says that the distance from this minus 1 of minus mu should be less than 1. So if we take, for instance, if we take, so if mu can be any complex number, so this just says that in the in the plane, in the complex plane, this should be I think I have a wrong sign somewhere. No, it's okay. So the stability region is some region around the point -1. So in the complex plane this is -1. It's a circle like it. So the Euler's method is stable here. And for our purposes, which is to integrate hyperbolic equations where the lambda is imaginary. So the points for lambda, the eigenvalues for the hyperbolic systems are here, in some region here. So this method is not good. That's why we saw that instead of having a solution going around in a perfect circle, we saw a solution that was growing like this. It's because we were here, somewhere here, and so it's not good. The solution is growing because this factor is bigger than 1. So here you have some exercises you can do. It's very simple. You can compute the same way the amplification factor for the Hoyne method or the midpoint method. Or you can find it the Runge-Kutta-4. That's harder calculation. I mean, it's a simple calculation, but it will take a while for the Runge-Kutta-4, and you can plot it. But we are going to do it with a program numerically in a second. So if all these methods, the Hoyne, midpoint, Euler, are unstable on the real axis, in the imaginary axis. But the Runge-Kutta-4 is stable. And the stability region of the Runge-Kutta-4 is something like this. It goes like that, where this point here is minus 2.7, I think. So all this region is okay. And this distance and this distance is similar. And then in this piece of the complex of the imaginary axis, you have stability. So this is a very good method for this reason. You can show that there are no second order method that is stable in the imaginary axis. You need at least a method that has a third order and four functions evaluation. I think you need 4 functions evaluation. But there are many. You could use, if you want to use implicit method, what are implicit methods? Implicit methods are methods, for instance, that depends, the evaluation of the function is also at the n+1 point, so you need to solve for it. So there will be the Euler method. There is an Euler method which is implicit, which is like that. Instead of evaluating this at n, you evaluate it at f up to bn+1, right? So for finding Bn plus 1, you have to solve this problem. You can use Newton, maybe this is linear, then it's easy. And for the linear case, what you can do is exactly, the method is this one. And so you rewrite it and it becomes Bn over 1 minus mu. So the amplification factor now is 1 over 1 minus mu. I'm doing the same trick that says that this you write as 1 mu minus 1. You see that for this to be bigger than, smaller than 1, you have to be outside this area. So the stability region of this method is all this. Right? So this is very good for these points. And all these points, if you have are solving some heat equation, for instance, where the eigenvalues are here. But the problem is that you have to, it's implicit, so you have to do something to solve for. Sometimes there are methods which are called IMEX, which are a mixture of implicit and explicit terms. And that happens, for instance, if you have some equation which has some linear part which is very big, so epsilon is very small, plus another part. So if you have this, you can solve for this part exactly. You can put the Bn plus 1 on the other side for this part. You can use Bn plus 1 here and Bn here. And then you get one of these IMEX methods. They are in the library, so you can use it. And for those cases are very good. Here is a nice exercise. You can do the same implicit one, which is like this. So you take, the method will be like that, like this. Delta t times f of Bn plus 1 times theta plus 1 minus. So you do convex linear combinations. Theta is between 0 and 1. So theta equal to 0 give you the standard Euler. Theta equal to 1 gives the implicit. And you can do combinations. And you can check this. For instance, if you want to solve the equation dy dt equals to, so the heat equation, k times Laplacian of y, you could do this in there are very nice methods where you use Bn plus 1 is equal to Bn plus a combination of theta times delta of Bn plus 1 plus 1 minus theta Laplacian of Bn. And this method, some of these methods are very good with theta equal to 1/2. And you have to solve this problem. So you have the Laplacian here. So this is 1 minus k Laplacian of Bn plus 1 is equals to 1 plus, for the 1/2 case, 1 plus 1/2, here is 1/2, 1 k over 2 Bn. And so you have to Laplacian. So you have to invert this. You have to take the minus 1 of this in this side, right? So this is an operation which is not trivial, but you can do it. And so you get a very nice method for the heat equation this way. Probably we'll do it near the end of the course. So this is more or less all what we need about ordinary differential equations to go to go to the partial differential equations. So there are questions? Are there questions? No questions? Let me look at the chat. Huh? No? Okay. So now we are going to present the lab. I think I have somewhere here the lab. Let's see. I think I have to go out of this first and find the lab. Oh, let me show you this first. I have a problem here. I think I have to close this and open again. Yeah. I had this problem yesterday. So this is how to compute the stability ratio. So you have a system like that. This is a one-step method. And so the stability region, and we are going to use it for this equation. So for this equation, the stability is like that, where you can compute this, say. So what you want to know is this value. Actually, now I realize that this is in Spanish. Okay. So this is the stability region is the muse in the complex plane such that this is less than 1. And to compute that, what we do is since we have this relation, what we need is this. So we can take Bn to be 1, and so the next value, the first value, is just this, right? So what we do is just that I think I have a version which is this version. It's in English. I translate it. So for instance, for Euler, you get the stability region is all mu such that this is less than 1. And I forgot to change this. So as I say, we just do one step, and then this number is just the ratio between the two solutions, the absolute values. So we are going to use this package, which is ordinary differential equations. It's a package that has hundreds of methods, all of methods, but practically everything you need is there, and plots. So we define the linear function here, and we create this stability indicator. Why? I have a mixture of things here. Oh. This is the one I want to run. This. Okay. So we create this function, stability indicator, which gives, given the mu and the method, produces the stability, the factor this 1 plus a that we have before, and returns either 1 or 0. If the absolute value of this difference is bigger than 1, then return 0, otherwise return 1. So the area where it's stable has a 1, and the area where it is unstable has a 0. And the way it does is take delta t equal to 1. So delta t is just, so mu is equal to lambda in this case. And then creates a problem. The problem is this probe is some instance, something that has many parameters there, that is created automatically by this package. And it's all the problem from, you put here the function, you put here the initial data, the time span, and the mu, which is lambda in this case. And then you choose the integrator, and the integrator takes the problem, the method. So here you put the method you want to use. The delta t, you have just 1, and you put adapted equal to false. This is so that it will take delta t equal to 1 no matter what. Because if you don't put that phrase, it will try to adapt the delta t so that the error is less than something. So if you want to keep the delta t fixed, you have to put this adapted equal to false. And then you step the integrator once. This is the one step. And the solution will be in this, where it is defined. I guess the u final is created inside the function, inside this integrator, seems to be. So the result is u final. The result of this will be a function u, and you take the integrator, the component u is u final. It says the result after a step, and then you say, oh, okay, absolute value of final is bigger than 1, then returns 0, otherwise returns 1. So here you have a region, define a region where you want to plot the result, and then you use this function, plotting function, heat map, that maps all the xy points and maps these things into the stability indicator, and you have the mu is here, the x is a real part, the y the imaginary part, and say you take Euler. And what you get is this thing here. If you see the 0 here is in this line, the -1 is in the middle, -1, 0, and this is -2, 0. If you do this for the Runge-Kutta-4, here the method is Runge-Kutta-4, you get some region like this, and you see this covers the imaginary axis, and the imaginary axis goes around here, crosses this here, comes like that and goes up. So you can solve up to some point here, 2.7 or something. You can solve with this method and it's stable. Inside this region is stable. And for the negative it's also like 2.9 or something, or 3 maybe. But it's a bigger region than the Euler's. Okay, and this should be stability. Indicator. So we are going to compute it for the seat. This is another method of fifth order. This is a very good method. So sometimes we use this instead of Runge-Kutta-4, and the stability region is like that. So it also contains a piece of the imaginary axis. And here there is another one. This is for a function that we are going to use when solving for shocks that has some nice properties, so we check that the stability region of this method is okay. Something we already knew. And this is stability region of that method. It also goes to 2 something. So these methods are in the same place where the homeworks are, so you can check on this. Or maybe not. I'll put them later on. I think these are in another place. Pablo, can you put them? I think this notebook is not. We can put in the lab. I'm not sure whether it is. I thought it was. But. So now we are going to look at the homeworks. Let me find it. I have to update everything here. So let me Maybe I have it here already. No. Labs. Lab 1. So here we have, this is the first lab. Ya te digo. Fíjate uno que está en inglés ahora. El que está en inglés. So this is the lab. No, this is not the lab. Why? This is not, sorry. Again. Where is the lab?
Pone atrás, fíjate en una que se llama Will, arriba,
Ah,
Will, lab 1.
okay. Okay. Here is it. Here, this is the. So this is important. You rename the file. You download it and put your last name, first name, lab one. This name. Okay. So that when you submit it, we know from whom it is. So everything you do has to be in the notebook, in the same note. So the objectives are that you build some simple integrators and apply them to problems in 1 and 2 dimensions, study conversions and determine the method Q factor, study the convergence region of the method, check the approximation errors both qualitatively and quantitatively, get familiar with other integrations libraries, get familiar with handling and analyzing solutions in moderately complex cases, study the stiff case and the Emacs method. This is the Emacs I mentioned before. So first you take the linear equation, solve it with Euler's method, and here is the implementation. Here you have a complete implementation of Euler. So this we give you. and then we do it more in the same way that I show you just with the library, so that you get used to this. So you create the Euler step. It's a function that just make the step only. And then you define this function, my other problem. Remember, the other was other problem only. This is my other problem to distinguish. But it's the same thing. It just gives it the f, the initial point, the interval where you want to integrate, and some parameters for the f. And what you return is this tuple, nothing more than that. It returns all these parameters again. And you have here the solver. That was a problem. This is a solver. And the solver has the same structure than this. But now, here, instead of having the Euler step, have the method. So you have to give the method. The method is how you go from one step to the next. Huh? So you can apply to the exponential growth. The parameter here is just lambda, and you have this. So the problem is the exponential growth is just y, t, lambda. This is a function, so you give the functions, you give the initial point, the time, and the parameters. Initial point is 0 up to 4. This is the interval. You put here a number of time steps and you solve. So when you solve, you put the dt, the time step, that you compute from the final interval minus, so the time interval divided by the number of steps minus 1, and you get a solution. And you can plot it, and you see that you get an exponential. But you see that after a while the exponentials are very different. And so here there are some questions and some things you have to do. 1A, 1B, 1C. And here, for instance, in the 1C, you have to compute the Q factor. And for that, you have to create the functions, the step functions, Runge-Kutta 2, Runge-Kutta 4, like the Euler steps. So you have to do these two functions. This is similar to this one, right? You do these functions, you change the method, and in the method you put this string or this string, and these functions. And now you consider this function that was the one that we discussed also, the bacterial growth. And now we work with the system of equations. You treat, for instance, the harmonic oscillator. You know the general solution is this, but you convert into a first order system, as we did. Consider these initial values, this parameter and these initial values. And you can use everything as before. The only thing is that you have to define, for instance, the initial position with two numbers, U0 and V0. It's not difficult. And that will be the end of the lab. Questions about the lab? We are going to have some discussion Let me put it here. We will this Thursday at 15 hours online. I will try to use the same Zoom that we are using now. Otherwise, probably I will use Meet, and I will send by WhatsApp. The direction of the Meet. But I will try to use a Zoom. we have to arrange with Tiago to have it. Okay, questions? Any question on the chat? Here? So let's take a break.
Profesor, para mañana,
La,
¿no quedó en las 2?
a las 2. ¿Vos cambiaste a 3?
No, las 14,
Okay.
Las 14.
Okay. Instead of tomorrow, we'll meet at 2. Okay, we continue at 10 after 10.